Most people have seen a periodic table. Now we're going to explain some very simple things that we can get from the periodic table and how we can use it for very basic chemistry operations. Before we look at the periodic table, we need to talk about what matter is. So matter is any substance that has mass and takes up space. That's one definition of matter. So look around you, see if you can see anything that is matter. What about something that's not matter? Well, if you look around, when we look around to see what is matter, you're going to see just about everything you see is matter. What about air? Is air matter? Does it have mass? Can you weigh the air? Yes, we certainly can. You can actually put it in a balloon and see how much it weighs, and depending upon what's present in the air, it will have different masses. And does it take up space? Well, obviously, if we can blow up a balloon, it's taking up space. So air is matter. Even though you can't see the air, it is matter. And what about things that are not matter? Well, generally the things that are not matter are considered energy. So there are things like light, sound, those types of things are energy, but we're going to be focusing on matter here. Other things that are not matter are thoughts or concepts. So for instance, love, it might matter, but it is not itself matter. Hate, war, those types of things. Those are things that are happening, or feelings, that type of thing. Those are not matter. They do matter in the world, but they are not matter. All of matter can be categorized into various types. For the moment, we're going to focus on just one type, and that is the element. Let's look at how those elements have been sorted within the periodic table so that they're easier to define and what kind of characteristics we can get from that periodic table. In 1803, John Dalton reproposed the idea that particles, known as atoms, made up the elements. After that, people started studying and hunting for new elements. By the mid-1800s, a large number of elements had been identified. Then in 1869, Dmitri Mendeleev decided to organize all of these new elements and find out what kind of patterns they made. So he found that some of them reacted with water, some of them were very stable, and he grouped them in that pattern. Originally, he grouped them in horizontal rows, and then a couple of years later, he developed what we now know as the periodic table. In that periodic table, one of the things he did is he grouped them vertically by the way that they reacted. So some of them were soft and shiny metals that reacted super violently with water. Other ones would dissolve in water, and other ones would not react at all. So he grouped them by how they reacted with each other and with water, and then he organized them after that by size or by atomic number. And back in 1869, when Mendeleev developed the periodic table, there were only 63 known elements. We now have far more. That periodic table is the one that we'll be using in this course. When he did this, one of the things he found is that there were some missing parts. There were some elements that were not yet known. Anytime he found a missing element, instead of just sticking something in that place, now he left that as a gap. And then later those gaps were filled as people discovered elements. And this was its predictive value, so Mendeleev's periodic table was particularly useful in identifying what new elements of which things were missing and helped us to find more elements. Over the years, there have been loads of different periodic tables that have been designed. These other periodic tables describe different factors of these elements. They're very important and they're very valuable for those people that are studying those details. So some people will use those other periodic tables. But in this class, we're going to be focusing on the one that was developed by Mendeleev in 1869 and has grown since then to include even more elements, so that now we have almost 120 elements in the periodic table. Later, we'll use this periodic table to help us predict how things behave. But for now, let's just figure out what the basic information that we can get from most periodic tables is. Most periodic tables will have these three parts present. On the top, they'll list the atomic number. That is, the way that we can identify each element is by its atomic number. Underneath that will be the element symbol, and of course you've already memorized the names and symbols. You kind of should recognize those. And it's generally one or two letters only for our element symbol. And finally we have the atomic mass. So this is an average mass of that type of element. And as a reminder, remember the average mass, which we call the atomic mass, doesn't tell you how much each individual one weighs, but how much they weigh on average. So if there were 100 atoms of palladium, they would average out to 106.4 AMU. But one individual palladium might weigh 106, another one might be 107, another one might even be 105. So on average, the masses will be 106.4. One of the first things to look at when we look at this periodic table is that the elements are arranged in order of increasing atomic number. So if we look at the periodic table, we start with hydrogen over here. It has atomic number 1. We jump all the way across the periodic table. We see number 2 is helium. Jump down, and one more row, we have number 3, lithium, and 4, beryllium. And we just keep going across the periodic table. So as we count, it goes 1 way over here, 2, then the next row, 3, 4, and then jump all the way across, and we get to 5, 6, 7, 8, 9, 10, and then we go down to the next row, 11, 12, jump all the way across, and then we have 13, 14 through 18. Then for the next 2 periods or rows, we see that the numbers just continue to increase numerically. Then when we get to period or row 6, we see that it counts 55, 56, 57, and then we have a jump down to 58 through 71. Sometimes 57 is included in that jump down, and what it is there's actually a gap there. We call that the lanthanide series because it starts with lanthanum. And in the 7th period, we see the same thing happen where we go 87, 88, 89, and then a jump down for 90 through 103. And these are called the actinides. The actinides start with actinium at atomic number 89 and continue on through lawrencium at atomic number 103. The lanthanides and the actinides are not really separate from the rest of the table. They actually should be placed within the table, but that extends the table so much that it makes it very hard to look at and hard to read. And so in this class, we will take out the lanthanides and the actinides, push that table together, and use the smaller version of the table, which is much more readable. As mentioned previously, one of the first things that Mendeleev looked at when he was designing his periodic table was to look at how they reacted. And so he found that certain groups reacted in a certain way. So we have group 1 over here, and all of those are soft metals, and they all like to react with water, except for hydrogen, which is sort of the oddball. But everything in this first column has one type of behavior. In the second column, they have a similar reactivity, but they are not the same, so they got a different grouping. And as you go across the periodic table, you'll see that each column has things that react in similar ways. So if I told you that lithium reacts with water, you would know that everything in column 1A reacts the same way, so we would expect sodium to also react with water. Now they might look a little bit different, but they have very similar characteristics. So those are what we call groups, and you might think of them as like your group of friends. Your group of friends might like jazz music, and your sister's friends might all like hip-hop music, and your mother's friends might like classical music. So each type of grouping likes a certain type of thing, and they all behave in a similar manner because they like those similar things. Another name for these groups is families. And families, similar to the way we have our group of friends do one type of thing, families do the same thing. So sometimes we're called families, sometimes groups. In a family, maybe we all celebrate by blowing out candles on a cake, or maybe you blow out candles on an ice cream, or maybe you have pizza for cake. Every family has their own traditions, and those traditions are considered family. They all follow the same pattern. Again, groups and families are the columns in the periodic table, and everything in the same column will do very similar types of reactions. On the periodic table, we have 2 categories of elements. One is called the representative elements, and the other one is called the transition elements. The transition elements are called that because they're transitioning from one type of representative element to the other, so they're called transition elements, and that's sort of the center section, and we call those also B group elements. The A group elements are the ones that are following the norms and are what we would call representative elements, and that's this first 2 columns and these last 6 columns. And the B group or transition elements are everything in between those two taller parts, and that includes the lanthanides and actinides. Within the A group, there are 4 groups that have special names. The first two, group 1A and 2A, and the last 2 groups, groups 7A and 8A, all have very common names. These common names are so common that I expect you to know them. So we're going to start with group 1A. Group 1A is commonly known as the alkali metals. Group 2A have the common name alkaline, notice there's an I-N-E at the end, alkaline earth metals, and the whole name needs to have all 3 parts to it. And then we go all the way over to here to group 7A, and we have the halogens, and the very last group is called the noble gases. They are also sometimes called the inert gases. The other groups don't have any special names, except that we should still recognize that those B group elements are considered transition elements. But we can see group 3, 4, 5, and 6 don't have any special names for those groups. So you don't need to know anything more about them except to call them group 3A, 4A, 5A, as we would consider it. So we know that the columns are called groups or families. The rows are going to be called periods. So we have period 1, 2, 3, 4, 5, 6, 7, and hopefully someday we'll see something in period 8. We're not there yet. So in the groups, those columns, we know that they were organized because they were found to have similar properties. Is that true of the periods? Well, no. The periods do not have similar properties to each other. Each element in the period is going to have a property related to its group, not to the period. So the periods don't have a lot of relationship to each other, except that we know as we go down the periods, the atomic number will be larger because we have the lowest numbers at the top, the highest numbers at the bottom, and that the size of the atom actually increases. So it gets bigger and bigger as you go down the periodic table. And that's how these periods were developed, how we know which one goes in which order. It goes by atomic number and by increasing size. So we should see that lithium is smaller and sodium is larger. As we go down the periodic table, the element gets larger and larger. The type of question you might see for this, maybe something like, give the symbol for a halogen that's in period 4. So you're going to look for the halogen column, and then you're going to go to period 4. We'll go down 1, 2, 3, 4, and we see that that is Br, which would be say is bromine. So the answer would be Br. So let's try a little more challenging question. How about, what is the atomic number of a alkaline earth metal found in period 3? And so for that, we're going to first go to the column alkaline earth metal, and we see that's column group 2A, so column 2. And then we're going to go to period 3, so we count down 1, 2, 3. Don't forget to count that first period with the hydrogen and helium. And we get to magnesium. So we know the element's magnesium. All we need to do is find out what is the atomic number. And then the atomic number is the one on top, and that will be number 12. Another common way of separating the elements in the periodic table is to group them into 2 patterns as metals or nonmetals. And then we have a third grouping which we call the noble gases. We'll talk about those in a moment. So first off, think about the metals. What kinds of things would be metallic? If you look around your house, what would be metallic? Well, you might see your sink. You might see pots and pans. You might see your door handles. That type of thing. Those are metallic. And how do we know it? Well, you kind of know it probably from your daily life, but you might recognize that they're shiny. They have like a metallic cling. If you check them with another metal, it might have a metallic sound to it. They might have, they're hard, they're solid, those types of things. Those things are our descriptions of metals, and we know that those metals are a certain grouping on this periodic table. Then we have another group which are called the nonmetals. The nonmetals are soft. They might be solid. Sometimes they're liquids and gases, but generally they don't seem to shine. They seem to be kind of soft and powdery, and they behave quite differently from the metals. So the metals and the nonmetals, one of the distinguishing characteristics is how they react. In much more detail in units 2 and 3, but we first need to be able to identify whether something is a metal or a nonmetal, just so that we'll be able to be in good shape for unit 2. There is a third grouping in this list, and those are called the noble gases. They are kind of pulled out from the rest of them. The reason they're pulled out is they don't behave like metals, nor do they behave like nonmetals, and that is because they behave like noble gases. They behave very differently. And what their behavior is that they do not react. And so that's why we don't list them as how do they react? Do they react like metals? Do they react like nonmetals? These ones don't react, so they don't react like either of those two. So how do we see the difference on the periodic table? The way that we're going to identify the difference is we're going to use this solid stair-step line. It starts here next to boron, and it goes down and then across, then down and across and down and across and down and across and down and across and down and across. And you can see it just kind of keeps following that stair-step until it gets to the end, and that is considered our stair-step line. We're going to use that as our dividing line. Over here we have our noble gases, which is that last column. Again, we know that by its name and by its behavior. So the last one is noble gases. Everything to the left of the stair-step line are your metals, so that's the vast majority of the periodic table is metallic. And then this little section in the middle between the noble gases and the metals is your nonmetals. So where does hydrogen belong? Well, if we continue up this stair-step line and go all the way across, we'll come to the other side of hydrogen. Hydrogen is considered a non-metal, even though it's in the column with the rest of the metals. Sometimes it does actually behave like a metal, but only under certain conditions. For the most part, we're going to consider it a non-metal. In this class, it's going to be considered a non-metal. There is one last grouping that the book mentions. We're not going to be focusing on that in this class, but I do want to talk about it so it doesn't confuse you, and because some of the homework online will have some questions about this. And that grouping is called the metalloids. So the metalloids are the ones that are touching the stair-step line for the most part. One exception is aluminum. Aluminum is considered to be a metal, and you can kind of see it because it's aluminum foil. You can see how very metallic it appears. But everything else that's touching on both sides of it, not just the corner, but has two sides touching that stair-step line, is considered actually a metalloid. So we'll see boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, and possibly tennessine and oegesium, which we don't really know a whole lot about because they are so little studied new elements. And what makes something a metalloid? Now, a metalloid is something that has properties somewhere between a metal and a non-metal. So we said metals were shiny and hard. And we find that some metalloids are shiny but soft. They might be powdery. Or we might see something that is a metalloid that we would say is hard and not shiny. So some of those things happen. One of the really interesting things about metals versus nonmetals is that metals conduct electricity and heat very well. Nonmetals do not. So we have these metalloids, and one of them is silicon. You may have heard of something called Silicon Valley. And one of the important things about silicon is that it is a semiconductor, and that's because it's a metalloid. It doesn't conduct really well, like you would see for a metal, but it does conduct a little, whereas you would see for the nonmetals, they generally do not conduct electricity. So because this is a metalloid, we are able to base all of our whole computerized systems on silicon because it's a semiconductor. And so we'll see that with all of these intermediary ones, those metalloids. They behave a little bit like a metal, a little bit like a nonmetal, and so their properties are not as well defined as one might expect. But in general, we know the metals are on the left side, nonmetals are to the right side of that stair-step line, and then we have the noble gases as a separate grouping. And for this course, when I ask you a question, I only need you to know metal versus nonmetal, and of course the noble gases, which are neither metals nor nonmetals. So here's a quick question. Is cobalt a metal or a nonmetal? Well, you need to know what cobalt is, and that's the symbol CO. We see it over here, and this is in the metal section. How about the element selenium, which has the abbreviation Se? Metal or nonmetal? Right, you should see that as a non-metal. What about germanium, which has the abbreviation Ge? Well, we see that that one is on the left side of the stair-step line, so in our course we're going to call that a metal. Yes, it is a metalloid, and in the online homework they may ask you if they give you that option, it would be a metalloid. But for my class, my test, we would say that is a metal. When we look inside of the periodic table cells, we almost always see three things. First, we always see the element symbol. That's big right in the middle, easy to spot. And then on top of that, we should see the atomic number. The atomic number is one of the ways that we identify which element we're talking about. In Unit 2, we'll go into more detail about where that number comes from. But the important thing is that the atomic number will identify which element we're talking about. For instance, if I wanted to indicate I had sulfur, I could say, oh, it's atomic number 16. Or if I wanted to say chlorine, it would be atomic number 17. So we can just look at that number on top and know which element we're talking about. Finally, the last one that is on most periodic tables is the atomic mass. All of the periodic tables that we will use in this class will have an atomic mass on the periodic table. I know there are some on the internet that don't have it, and many periodic tables have a lot more information. For us, this is the version that we'll be using, except it won't say the element name at the top. The atomic mass, sometimes known as the atomic weight, is the weighted average of the masses of all of the isotopes of an element relative to the mass of carbon-12, which is an isotope of carbon. Those units are going to be atomic mass units. Well, that seems like a lot to say, so that's the definition. But what we need to know is what are the two major things that we find important about this. The first thing is that the measurement we're going to be doing is going to be in atomic mass units. We use atomic mass units because the numbers that we see for an atom are really tiny. We're not going to be able to weigh them in grams, so we use a different scale called the atomic mass unit. And again, we'll talk more about that in Unit 2 and where that number comes from. But for the moment, we just need to know that all measurements that we see on the periodic table here are measured in atomic mass units. Okay? And then the second major thing here that we're going to notice is that it says it's the weighted average. So when we say the weighted average, that means that you see this decimal point here. It tells us what percentage of each type of isotope we have. What is an isotope? Again, we'll talk about that in Unit 2. For now, all you need to know is that it's a weighted average. So let me give you an example. If I have 100 people and 50 of them weigh 100 pounds and 50 of them weigh 200 pounds, the average would be 150 pounds. But if we have 25 of them that weigh 100 pounds and 75 of them weigh 200 pounds, the weighted average would go higher, it would be closer to the 200, and now the average would be 175 pounds. I'm using really simple numbers there. Hopefully that makes sense to you. So the number of each one changes the average. Even though the numbers are 100 and 200, the average has shifted closer to 200 because we have more of them. So we call that a weighted average because there's more of one of them, it shifts towards that direction. If I had 100 people and 75 of them weighed 100 pounds and 25 of them weighed 200 pounds, we would find that the average mass, the weighted average, would be 125 pounds, closer to the 100 because there's more people that weigh 100 pounds. Obviously, people weigh numbers in between. When we're looking at these isotopes, we're going to see that the numbers are very consistent. So in the case of chlorine, there are two major isotopes. One of them weighs 35 AMU, the other one weighs 37. If we look at this average, weighted average, you should be able to see that it's closer to the 35, which means most of the isotopes that we have are going to weigh 35 AMU, not 37 AMU. Again, you're not going to have to know anything about that for this test. We're going to see more of that in Unit 2, and we'll define where we get those numbers and things like that. For this unit, you really only need to know two things. That the number on the bottom, the atomic mass, is an average mass, but it gives us an idea of how much something weighs, and that it is measured in AMU, atomic mass units. That's what we're going to be using in our next section, which is about chemical formulas and calculations we can do with those formulas.